I'm going to spend these 4 lectures talking about refinements to the branch and cut ideas. And the first one is exploiting separability, or exploiting problem structure, and that's going to be recurring theme. One quick question. What do you think is the worst case complexity of outer approximation? So quick informal test. So we have outer approximation. That was one of the algorithms. And let's say we have n or p binary variables. What do you think is the worst case complexity? Anybody? What? 2 to the power p. Excellent. Good. So you can now ignore the next 3 slides. So here's an example that shows that this is the case. This was actually not easy to cook up, this example here. The example is an optimization problem where we minimize a constant function subject to just one quadratic constraint and over the unit hypercube of binary variables. And on the right here is a picture that shows the non-intersection of the unit ball. So this quadratic constraint is a unit ball centered at the point a half, a half, a half, a half, with this radius here. And the unit hypercube is sort of drawn here as well. And so what you see is that if you want to be both inside this ball or this sphere and at one of the vertices of a unit hypercube, then that's not possible. So they're all excluded. And in fact, if you did outer approximation, then what we do pictorially is we pick one of the integer assignments, this one here, for example, at the top left. We solve a nonlinear optimization problem. In this case, that's vacuous. So we just compute the separating hyperplane, and that will just cut off one of those vertices. And because there's 2 to the n of these, you have a counterexample that outer approximation visits all 2 to the n vertices. Okay, so the authors who did this also studied this in a more general setting. So in particular, they looked at a function that is smooth and convex. It's a real function from the reals to reals. And inside the function, there's a collection of linear functions, basically. And each function has its own linear function. And that's exactly the structure that we had on the previous slide, right? This is I have a convex function, x squared, the sum of squares, and inside are these simple affine functions. And then it turns out that you can write this constraint equivalently as by disaggregating it. So you're introducing additional variables, in this case yj, these are also continuous variables here, that represent each of these individual functions here. So yj just represents each of these individual functions. And separating out in this way is actually stronger. It can be shown to be tighter. And so I'll show you this on the little example that we had, which was the counterexample. So in this case, the disaggregation or the separation of these functions is to start off and introduce each individual nonlinear function and write it separately in its own format. And then have the constraint just over the yi. Okay, so if I do that in this example, then there's a little trick. In fact, if I linearize about 2 points, so I take a point, my first point, y1, which is, or x1, which lies in 0, 1 to the n, and x2, which is just the vector of all ones, minus x1. So that's the complement of the first vector. If I do that, if I take those 2 vectors and now substitute them and compute the linearizations, then I get this set of linearizations here. And the reason I get those is we can just quickly go back. And I need to linearize these functions here. So I need to linearize xi minus a half squared less than or equal to yi. And so I'm going to do this real quick. So the linearization is if I call this function here for the moment gi of xi, then the linearization is the value of gi plus the gradient of gi times x at a particular point x hat, xi minus xi hat, less than or equal to yi. And so I now have two cases. So either if xi hat is equal to 1 and xi hat is equal to 0, the function value is the same. So in both cases, gi hat is just a quarter. And the gradient of gi at this point is 2 times xi minus a half. So that'll be 1 in the first case and minus 1 in the second case, I believe. You can check that real quick, make sure that's correct. And so now if I put all this together, then for in the case where xi hat is equal to 1, I get the constraint that I have a quarter plus xi minus 1 is less than or equal to yi, and that's equivalent to exactly what I have there, minus 3/4 plus xi less than or equal to yi. And I hope that's one of the constraints that we have here. Okay. And so the interesting thing now is if I now take any other point, xi, or this particular point that I had before, then and I plug it in here, then yi has to be non-negative, because either xi is 1, in which case yi is greater or equal to a quarter, or xi is 0, in which case yi is also greater or equal to a quarter. In fact, yi has to be greater than or equal to a quarter. I have n of those. I sum them all up, so the sum of the yi is greater or equal to n over 4, which violates the original constraint. So this is great. So previously I needed 2 to the n cuts. Now I just need 2 special cuts. I need to have the cut around my point and then the complement of that point. And in general, that's maybe not obvious that you need to do that, but you can see that even if you don't do this, you will cut off a lot more points by choosing this disaggregation. Okay, and this idea has also been generalized to the nonlinear case. So you can do a little bit more when you're looking at nonlinear functions, just making sure that the overall constraint function that you construct here is still convex. So here, G is a general non-smooth function that has p values, and H is smooth, convex, and non-decreasing. Right? If we're decreasing and increasing, then you could get a situation where you have 2 humps, and so it wouldn't be a convex function, the resulting function. So in general, the composition of convex function is not a convex function, but if the outer function is non-decreasing, then you get a convex function. And now you can again introduce a new variable, y equals g of x, and disaggregate the constraint, separate the constraint. And the reason you don't need to write equality, in fact, you should not write equality here because that would make it non-convex, is because this first constraint, because h is non-decreasing, gives you an implicit upper bound that is pushing down on y, and g of x is pushing up on y. And so, in fact, what you get at the end that with these 2 constraints together, it falls out automatically that y is g of x. And it's possible to show now that, again, when you create outer approximations, when you create outer approximation cuts. You can either create a cut for the original problem or for this new problem where you disaggregated the constraints. And because you disaggregated the constraints, you have more of them, and it turns out you can show that these cuts are now stronger. So the second formulation, this disaggregated formulation here, is a stronger formulation than the first formulation. So that's interesting. It means that it's a good idea to maybe disaggregate constraints, separate them out. There's another advantage to it. It also makes the problem sparser. So because you're separating these functions out by variables, the Jacobian of h no longer depends on x, whereas here the Jacobian of h depends on x through g, and so that's a much more nonlinear coupling and could be much denser potentially, whereas this is more Jacobians that are sparser. But again, in general, what you do is you, in the first case, the linearizations that you get is weaker than the second one. Okay, and so for the last 10 minutes or so, I wanted to walk again through an example that Ashutosh showed earlier, but again show that you can generalize this to nonlinear functions. So this is now a very simple mixed integer linear constraint. There are two variables. There is a continuous variable and then a binary variable. And what we're going to look at is we're going to look at what happens if we fix this binary variable either to 0 or to 1. So if I set my my binary variable to 0, then this first constraint here says that x1 is less than or equal to 30. So that's the constraint. That's this blue constraint is up here. But because I have also an upper bound of 14, the way where this blue constraint intersects the x, the sort of horizontal axis, is at 30. So that's very loose. On the other hand, if x2 is equal to 1, then you do the arithmetic and x1 is less than or equal to 9, so that actually cuts off something here. The feasible set of this original problem is the union of these two red lines, and the continuous relaxation is the green area that I have here. So now it seems clear that what you really want is you want this constraint here, or you want this set here, this red set here, which is the convex hull of these two feasible sets that we had, the union of these two feasible sets, which is the two red lines. And so you can get that by changing the coefficients. So you change without changing the problem, you can change the coefficients. In fact, you change the coefficients on the right-hand side. So you can reduce the 30 down to a 14, and that's exactly what you need now. The 14 minus 5 is still 9, that's still valid, and down here, if x2 is 0, then you're less than or equal to 14. So the constraint is now tight, both when x2 is 0 and when x2 is 1, which means that you have a convex hull. Okay, so this is clear, and the MIP solvers will do this for you. But the interesting part is that this can be generalized to nonlinear functions. And so in many problems, what you have is you have a nonlinear function on the left-hand side, and then we have this indicator variable x0 on the right-hand side that switches the nonlinear constraint on and off. So if x0 is 0, then it switches the constraint off because m is a large constant, and the nonlinear function is well below m, so the constraint is switched off. Okay, so one way to tighten this is to look at what happens when you substitute x0 equals to 0 on the right-hand side. You can check whether this m is tight enough. And the way to check is to compute the upper bound of the left-hand side over all the feasible points that you have, so over all the continuous feasible set. But this is hard because typically we like our functions to be convex. So if C is a convex function, then you now have to maximize a convex function. And that's a very hard problem, or a much harder problem, right? We have a convex function, and now finding the max of this function in many dimensions is really quite hard. But if you could do this, then you could tighten the constraint. You could now replace the big M by this tightest upper bound. So that's not really what you want to do. Instead, there is an alternative, and that often happens in many problems where, in addition to switching off the constraints, you also turn down all the variables in the constraint. And so you can think of this as being, there is a set of constraints which describe the physics of a particular block of equipment, for example, a distillation column, and then the variables are the individual flow rates or heat or temperatures inside your distillation column. And so when you don't have the distillation column running, when you switch it off, when x0 is equal to 0, then you don't need to worry about what value these variables take, and you might just as well set them to 0. So flow rates could be set to 0 because it doesn't matter what they are. So this is a structure that occurs very frequently in mixed integer nonlinear optimization. And it's also known as an implication inequality. So when x0 is 0, then all the other x's are also 0. And now it's much easier to tighten because now you don't need to optimize over C. You can just evaluate C because you know what the value of the variables is when you set x0 to 0. So when I set x0 to 0, then all my variables are going to be 0. So I just need to look at the evaluation of my nonlinear function C. And if this is less than m, then you can again tighten this. And so there's no need for this maximization. Okay, so these Presolve and reformulation techniques are really important, and they've been studied in mixed integer linear optimization for a long time. There's a very good paper by Martin Savelsberg. We'll run BibTech and put the proper slides up on the webpage later on, so you don't have to guess what the references are. There's a number of Presolve functions that are important. All of this is very tedious, so this requires a lot of looking through computational graphs, looking at code, and finding, fixing, and removing variables, and making sure you capture all the cases. That a constraint can be rewritten by just multiplying it by -1, for example, equivalently, and so on. Okay, here's a really cool example that Ashutosh had when he first implemented this. So he was looking at a test problem, a synthesis design problem, a chemical engineering problem from the Carnegie Mellon test set. And if there's no Presolve, then it just takes forever to solve this problem. There's a lot of constraints. If you do some basic Presolve, then there's a little bit of fixing that you can do, but you're still taking a long time to solve this problem. But if you do the full Presolve, and in particular, if you take advantage of this trick that was here, where you're switching units off and you're tightening the upper bounds on these units, then this becomes the tree that you now search. So here's the tree after 360 seconds, and here's the tree after a full Presolve that Ashutosh did. So you just search this little tree, and you get down to 2.3 seconds. And that then shows up in sort of performance profiles, so you can really show off now and say, look, we have, if we don't do, there's the other solver that we were comparing with at the time, BonMin. Here's Minotaur without Presolve. It's sort of comparable to BonMin, but if we do Presolve, we're up here. This is known as a performance profile. I didn't define it here. Essentially, it summarizes results for dozens or hundreds of nonlinear test problems, and it provides you with a probability distribution or density that your solver runs within at most a factor 4 of the best solver. And in particular, on the axis here, it tells you on what percentage or what fraction of problems you're the fastest solver. And so on about 80% of those problems, Minotaur is faster than any of the other versions. On the axis over here, it tells you the reliability of the solver in terms of what fraction of problems you're able to solve. So there's still some problems we can't solve. Okay, so this lecture was really about looking at a worst case example for auto approximation. That was this ball inside the hypercube. And then from that, learning from that there's a way of rewriting the constraints, disaggregating the constraints, sort of separating the constraints out, and then performing linear outer approximation separately on each of those little pieces. And that's a really powerful technique that helps solve problems much, much faster. And then in the second part, I showed you the small example that you also saw earlier, where coefficient improvement helps a lot. And this is something that's worthwhile doing, especially at the start of a solve. And so when you're building your own solver, what you want to do is you want to ideally build on other tech people who have done these things before. So the Presolve is tedious, but it's very effective on many problems. And so if you have any questions, I'll be happy to answer them. Yes?
Go to the part where max of C, instead of solving max of C.
Yeah.
Here, so how do we calculate equation? Once we know that C, 0, 0 is
Okay. So let's do that real quick. I need to remind myself too. So now, what we know now is that we know that, well, we could just replace m by this upper bound. So instead we could write, I think this is valid, C of x1 up to xk less than or equal to C evaluated at 0 times 1 minus x0. Is that right? So if x0 is 1, then the right-hand side becomes 0. And if x0 is 0, then the right-hand side is C of 0, and the left-hand side is also C of 0. So that's valid. And the left-hand side is C of 0 because if x0 is 0, then all my variables here, if x0 is 0, all my variables are 0. And so the left-hand side evaluates to C of 0, and the right-hand side is C of 0. Okay? Any other questions? If not, let's take a 5-minute break again. Oh, you're scratching your head or you're asking a question?
If C of 0 is 0, then it's a redundant constraint.
It's what?
If C of 0 is 0.
Yeah. Oh, if C of 0 is 0.
Then it's a redundant constraint. Which one is redundant? The first.
Oh, we don't know what C of 0 is. It's
if it turns out that C of 0 is 0.
correct, yes, that's correct. That's a good point, yes. If C of 0 is actually 0, then you still need it in the other case, I think. But you don't need to switch it on and off with the binary variable. So yeah, if C of 0 is, or if it's less than 0, then you don't need to have a binary variable here. That's maybe something you can remove.